Hello. Good morning, everyone.
Good morning, ma'am.
Good morning. So let's start with today's session. So as requested by you, I'm going to illustrate the forward feature selection algorithm initially with some examples so that you can understand how this algorithm works, and then we'll go for principal component analysis. Right? So we have seen this algorithm earlier, forward feature selection algorithm. So under wrapper methods, we are having discussed this algorithm. So what the algorithm does is, it begins with the empty set, and whatever are the available features, these features are being added to that set to come up with a subset of the original feature set that is providing us the desired accuracy. Right? So we have seen this algorithm, these steps earlier. So let me once again go through. What we have initially is a feature vector S, original feature vector X. And this original feature vector X is comprising the features like X1, X2, X3 up to Xn. Right? So we are having n number of features. Those are describing every instance in our data set. Right? Now, what we are going to do is, out of those X features, we are going to form a feature subset F. Right? In every iteration. And we are going to modify this feature subset F in every iteration. Associated with this feature subset F, we are having error that is denoted as E of F. Right? So F is a feature subset that we are computing, and E of F is the error associated with that feature subset. Right? So what our algorithm says, our algorithm starts with initializing this feature subset F by an empty set 5. So we are initializing F equal to 5, right? And we are initializing this error parameter E with some large value. Okay? Then what we are going to do next is, we are going to repeat some process till we find that the difference in the old error and new error is greater than some threshold. So threshold is a small number that we are going to pick. Right? Now, I'm going to illustrate this algorithm step by step so that you can understand. Okay? So, for every I, how many features we are having? N features. So, for every I, we are going to train the model on training set. So we are having defined the training set. Every instance in the training set is described with n number of features, and we may have n number of observations or instances in our data set. Okay, so we are going to train the model on this training data set with m observations. Right? But what we are going to do in every step is, whatever subset that we have selected F, right? We are going to train our machine learning model with those many features for every instance. And we are going to compute this error E with respect to the feature set under consideration. To compute this error, we are going to make use of the validation data set. Right? So we are training our model with training data set, and we are going to evaluate our model. We are going to find out the performance of our model with validation data set with respect to the subset F that we have selected in every step. Right? Now, for every feature that we are going to add into our subset, we are going to compute this error, right? And whichever is the feature that is producing the smallest error, minimum error, that feature we are going to select and add in our earlier subset, right? So I'm going to demonstrate now this entire process. Okay, so let us assume now that we are initializing our subset, feature subset, as the empty set. That means we are not having any feature right now at the initial stage. And as I stated, we should have this error assigned to some large value. So let us assume that we are assigning this error to some large value, say 9999. Okay, now what we are going to do next is, we are, see here, for the sake of understanding, I am going to prepare here one table. So we are having here I value, then we are having set F, and we are having error associated with set F. Okay, so as per the algorithm, we are now picking up I equal to 1. That means we are picking up the feature x1, right? So earlier my feature set was empty. Okay, now let us assume that in our feature set, as I have picked up x1, I am having this x1. Okay, now with this x1, I am going to train the entire machine learning model, right? So if I am having number of instances, say m equal to say 100 instances I am having, let us assume. Okay, so what I will do is, for every instance xi, right, I am having x1 instance, x2 as second, and so on, and up to x100. So I am having 100 instances. So if I have selected this feature x1, what I will do is, from this first instance, I will select the first feature, that is x11. Instance, I will pick the first feature x12 and so on. Correct? So x100. So these are my training examples, 100 examples. And out of those 100 examples, I'll be picking up only the first feature x1. Right? And this x1 is forming now my subset. So for this x1, I'm going to train my model and I'll be finding out the error. Okay, now let us assume that this error along with this feature subset x1 is, let us assume that it has been computed as 50. Okay, now what next I'll do, I will pick, I'm going to iterate through. So in every iteration, I am having the new value of I. So I gets incremented by 1. So I equal to 2. So obviously, if I equal to 2, I am having the feature x2. So now what I will do is, for this feature x2, I am going to train my model. Right? And once again, I'll be computing the error. Now, let us assume that this error comes out to be say 10. So similar process I'm going to repeat for x3. I'm going to train my model and I'll be computing the error. So if I'm having n number of features, what I will do, for every feature now, I'll be computing the error. So in this iteration, in my subset, I am having only one feature. Please remember that has been picked up. Okay. So let us assume that these are the associated errors, those we have computed. Okay. So up till this, what we have done is this part of the algorithm. Okay. Now, what next we are going to do is we are going to find out of all those n errors I am having now associated with these n subsets, right? So what I will do is I will find out the minimum error. I'll be finding out the minimum error out of all those n errors. So which is the minimum error here? Yes, which is the minimum error in this particular example? Yes. Are you able to understand?
X2.
Error, minimum error is 10. Right?
Yeah,
So what?
10.
10. So we are using this statement to find out the feature that is giving me minimum error. Right? So J equal to argmin I E of F union Xi. So this E of F, so here my F is having these features, and for every feature subset F, I have computed the errors. So I have looking at which error is minimum out of all those. So I come to know that this error 10 is minimum. So what I will do is I will look for the associated value of I with respect to this minimum error, and this associated value is 2, right? So what I will do next is I will come up with this J value equal to this 2, that is giving me, so this is the feature number that is giving me the minimum error. So if now J equal to 2, that means Xj is equal to x2, right? So here that is this new f old f union this xj. So old f was empty, right? So empty set union this xj is x2. So now my feature subset after this first iteration is having this feature x2 that I have selected. Okay, now what next? I will check now the errors. So associated with this x2 feature that we have selected, the error is 10, and the old error that we have assumed was 9999. So what I will do next is I will find out old error minus this new error. So new error that we have computed here is equal to 10. Right? So old error is 9999 minus this new error is 10. So it comes out to be 9989. Right? Now, let us assume that we are having some small number as the threshold. And let us assume that this threshold is being selected as say 0.1. Okay? So what we want is if error is greater than this 0.1, then we are going to repeat this process. Okay? Now, in this situation, what is the error? It is 9989, difference in error. It is 9989. So whether it is greater than 0.1, that is the threshold, yes, it is greater than. So what needs to be done is we need to repeat this process once again. Okay, so now in the next iteration, what will happen? in the next iteration, I am having my feature set f that we have computed earlier in the earlier step. So my feature set here is now x2. And what is my error? Error is 10 for this iteration. Okay. Now with these f and e values, now I am going to iterate through this loop. So what next I'll do is, once again I'll be having I value, then what I will have f value. So here my f will become now old f union xi. Okay, and here I'll be computing the error associated with this f union xi. Okay, so my I value, once again I'll begin from 1. So f union xi. What is f? It is x. So xi I am adding x1 in the feature subset. Now with these two features I am going to train our model, and we are going to validate our model, and we are going to find out the error. So let us assume now the error comes out to be say 20. Now for I equal to 2, I am not going to do anything. Why? Because x2, feature x2 is already been selected. Okay, so we are not going to do anything with this x2. So for 3, old set f, and I am adding now x3 in my set, and I'll be computing the error. Right? So let us assume that this error is say 7. Then I'll repeat the process x2, x4, say error is 15, and so on. I'll repeat this up to nth feature. So x2, xn, and let us assume that the error is 20. So once again, we are done with all the features. Now the same process is being repeated. So what we are going to do? We are going to find out the minimum error out of all those. So once again, if we look at the minimum error, we get that this 7 is the minimum error out of all the errors those we have computed. Right? And this 7 error is been obtained after adding this third feature x3 into my earlier feature set. Right? So with this statement, I am going to find out now the value of j, and this value of j is now 3. So my xj becomes x3. So what I am going to do is old f union this xj will become my new f. Right? So what was old f? It was x2. And what is this xj? It is x3. So my new f is a feature subset with two features, x2 and x3. Right? And the error associated with this feature set is 7. Okay? Now, what was the old error? That was 10. And what is this new error? That is 7. So 10 minus 7, it comes out to be 3. So whether this 3 is greater than 0.1, that is our threshold? Yes. So once again, if it is greater than the required error or the difference in error, we are going to repeat. Right? So what next we are going to do? In the next iteration, now my f becomes x2, x3. The error is 7. Okay. Now, once again, I'll be following the same process. So, I'll be having all the values of I, f union xi, and here I'll be computing the error associated with f union xi. So I value 1, So what will be my F union Xi? Yes, anybody? What will be my F union Xi? Yes. For I equal to 1, what would be F union Xi?
x2 x3
X2, X3 and union Xi means union X1.
x1
So X1. So I'm adding now X1 into the earlier set. Right? And I'll be computing the error. Okay? So let us assume that this error comes out to be 13. So once again I'll be repeating the same process. So for I equal to, we already have x2 in our feature vector. So we need not do anything for that. For I equal to 3, we are already having x3 in our feature vector. So no need to do anything. So for I equal to 4, right? My old feature vector is x2, x3 and I'll be adding x4 into that. With this, I'm going to train my model and I'll be getting some error. Okay? Say 5. Then what I'll do next is I'll repeat this process. 5. So x2, x3, x5 and I'll be getting some error. Okay? Then I'll repeat this up to n. So x2, x3 and I'll be adding xn and I'll be getting some error, say 50. So once again the same process we need to repeat. So once again what we are going to do is we are going to find out the minimum error out of all those. So here we find that this is the minimum error that we are getting 5 and the associated feature is x4, right? So obviously what we are going to do is we are going to have this j value equal to 4. So my xj becomes x4. So we are going to have this union of xj. So our new feature subset will become x2, x3, that was our old, union this x4. Right? So our new feature subset is now x2, x3, x4. Right? And the error associated is this 5. So my old error was 7. My new error is 5. So the difference is 2 and this 2 is still greater than the threshold point 1. So once again, we need to repeat this process. Correct? Now, let us see one more iteration and then we'll stop this demonstration. Okay? So, as we need to repeat this process, feature vector f is, or new subset rather, is x2, x3, x4. And the error that we are having is 5. Okay? Now, same process gets repeated. I, F union Xi and error associated with this F union Xi. So I is 1. So F union Xi will become X2, X3, X4. That is my old F. And union this Xi means X1. Okay? And the error associated is say 10. Now, 2 already there in the feature set, 3 already there in the feature set, 4 already there in the feature set, 5. So old feature vector, that is x2, x3, x4 and now we are adding this x5. Okay. Suppose this error associated is say 7. Now 6, so x2, x3, x4, that is the old feature vector and we are adding now this x6. Okay, now let us assume that we are having here the error, say 4.99. We are going to repeat this process till nth feature. So x2, x3, x4, xn, right? And suppose the error is 8. Now, if we look at this sample computation, what we understand is for the feature 6, I equal to 6, we are having the minimum error. So we are going to pick this value of j as 6. So my xj becomes x6. Correct? So my feature subset, new feature subset becomes old one union xj. So it becomes old one, that is x2, x3, x4 union xj is my x6. So new feature subset becomes x2, x3, x4 and x6. Old error was 5. New error is 4.99. So what is the difference now? 0.01 is the difference. So we are going to compare now the difference in the error, right, with our threshold. So what is our threshold? 0.1 that we have decided, right? So whether this 0.01 is greater than this 0.1, that is the threshold that we have selected. If it is greater, then we need to iterate, and in the next iteration we'll be getting the new feature subset. But as this condition is not satisfied, that means the decrease in error is acceptable now, right? So as this condition is not satisfied, see here in our algorithm, if decrease in E is greater than threshold, then we are going to repeat this process. But if this condition is not true, then what we are going to do? We are going to end up the process, right? So this is our terminating condition now, and this is how we are ending our process. And what ultimately we have got? We have got this particular feature subset out of this forward feature selection method, right? So for this particular example, we will say that we have obtained this feature subset x2, x3, x4, x6, right? And we are going to finalize this feature subset, and further we are going to train and test our machine learning model. So this is how from n number of features, right, we have come up with these 4 features.
Yes, ma'am.
So in every outer iteration, so we are having 2 loops here, right? So in every outer loop, we are picking up 1 feature out of all those that we have. Is that correct? In every outer loop, so this 1 column is meant for 1 outer loop, right? So in every outer loop, we are going to pick up 1 feature, right? And this is how we are going to iterate through till we are having the desired error, right? So our limiting condition is like this. So we are, if we plot the error, then we are having something like this. So initially we are having large error, and in every iteration we are having some smaller errors. So whenever we find that the error gets stabilized, right? So the error in 2 consecutive iterations is not significant, or difference in error is not significant, then we are going to stop that. So probably if we are having this kind of a curve, at this point it may happen that the error gets stabilized, right? So we are going to stop here. And at this point, whatever is my feature subset that I have obtained, I'll work with that feature subset. Okay? So I hope you must have understood this forward feature selection algorithm. The backward feature selection algorithm is exactly opposite. Here we begin with the empty set. In backward feature elimination algorithm, we begin with the entire feature vector that we have, right? And then we go on removing the features in the similar way. Okay? Fine. So let us proceed now with the feature extraction method. And as I stated, we are going to focus upon this principal component analysis. Okay? Now, we have seen the concept of feature extraction earlier. So, in feature selection, what we did in feature selection, whatever is our original feature set, we selected the features out of that original subset, and we come up with the reduced number of features, right? So original features we are keeping as it is, but we are selecting few of the features out of the original features based on some criteria. Now, in feature extraction, what we are going to do is the original set of features is being transformed, or it is being projected into a new subspace which has the smaller number of dimensions. So we are going to have a projection to n-dimensional space, and originally it is having n dimensions, where m is less than n. We are going to project our original features, right, in a new subspace with the dimension m such that m is less than n. So if I am having the original feature vector with n features x1, x2 up to xn, in feature extraction we are not going to select any of the feature as it is, but we are going to transform those features as y1, y2 up to ym, wherein this y1, y2, ym is actually the function of this original feature set of n features. So by having some combinations, some transformations of the original features, we are going to come up with less number of features y1, y2, ym. This is what our feature extraction method is. So in feature extraction also, we are coming up with m dimensions which are less than the original dimensions.
Yes, ma'am.
Fine. So simply I am going to introduce the concept of principal component analysis, and then we'll conclude this session, and in the next session I'll give you the exact idea how it works. Okay, so see here, let us assume for simplicity right now we are assuming that our feature vector x is having only two features, say x1 and x2. That means our original space is two-dimensional. Okay, so let us assume that these are the samples. Okay, those we have in our two-dimensional feature space. So these samples are describing actually our data set. Okay, and what we are going to do is we want to transform this two-dimensional feature space into, say, one-dimensional feature space. What does this mean? Right now, we are describing every instance in our training data set with two features, x1 and x2. Right? And what I want is, I want to transform now this feature subspace with two features such that in new one-dimensional feature space, this every instance will be described with only one feature. I want to reduce the dimensionality. So this is one simple example just to understand. Initially, we are having this space which is 2D and we want to convert it into 1D. Okay, now how to do that? So what we are going to do is we are going to transform the features in two-dimensional feature space into the one-dimensional feature space. So how to do that? Let us assume that we are having this particular line of projection, right? So please see here, this is my line of projection and this is not the line of regression. Don't have any confusion in this concept. We are not at all talking about the regression here, because you may feel like if I am having such kind of a line, this is a regression line. But no, this is not the regression line. I am picking up some line and I want to project my 2D data with respect to this line of projection. Okay, so how I'm going to do that? So I have picked up this particular line. So what I'm going to do next is I'll be computing now, right? I'll be computing now the error. Projection error. So what is this projection error? Whatever is my instance, I'm going to drop the perpendicular onto this particular line. Right? So this is the perpendicular onto this projection line. If this is the instance, I'll be having this perpendicular to this projection line and so on. So with respect to every instance, now I have dropped the perpendiculars to the projection line. Right? And these distances now between the projection line and my instance becomes the projection error. Right? And what we want is, we want to minimize these projection errors. In regression, what we did, we have found out this distance. If you remember, if this is the instance and this is the line, we computed this vertical distance. Right? In this projection or in this concept, we are computing this distance, which is perpendicular to my projection line. In regression, we used to compute this distance as error. Fine. So now, with respect to this line, we have computed the projection error. Okay. Now, let us assume that we are having this another line. So with respect to this line also, what we are going to do is, once again we are going to drop the perpendiculars from this instance to this line of projection. Okay, and we'll be computing the error. So obviously in this particular example, if we are having these two projection lines and if we try to compute the projection errors, obviously we may say that this particular line, red line, is giving me the minimum error, projection error. Right? Because these projection errors with respect to this particular line are significantly high than the earlier one. Okay? And that is how we are going to pick up. Right? We are going to pick up this particular line which is giving me the minimum projection error. So we are going to find out a vector onto which to project the data so as to minimize the projection error. Right? Now, this particular line that is giving me the minimum projection error. So what I'm going to do is I'm going to project all those samples onto this line. So simply I'll be moving this sample or this instance to this line. I'll be moving this sample to this line. So this will go here, this will come here, and so on. So every sample, every instance is being projected now onto this vector, onto this line. Right? So if we try to flatten this line, what we get is every sample is being placed like this. So earlier, my samples, my instances were described using two values x1 and x2. And now, after projection to some new dimensions, new space. So earlier it was r square and now it is r. So this is one dimensional space and earlier it was two dimensional space. So in one dimensional, my samples are being transformed like this. Right? So all the instances are being transformed from 2D space to 1D space. So each instance now is being described with a single value. Got it? So with this concept, basic concepts, right, we are going to illustrate our principal component analysis algorithm in the next session. Right? That will help us to reduce the dimensionality of our feature vector. Okay? So let's conclude the session today, and in the next session we'll be focusing upon PCA algorithm actually. Okay? So let's stop. Thank you.